Swayam Prabha. Digital India. Educated India.
Okay, you can continue with your questions. Yesterday we did something, right? So yesterday in the fag-end we discussed about lithium-ion battery charging, discharging. You understood, right? Integration? Intercalation, yeah. So you understand without disturbing the crystal structure how we add or subtract ions into the structure. That's basically the energy storage by which you put energy in the battery. Okay, now I heard that in +2 the solid state chemistry chapter is removed, is it so? Okay, it's one of the wonderful chapter, they removed it. Okay, then what else today you want me to teach? You have questions? No question? Yesterday you had a lot of questions. You can continue from where you left. Huh?
So yesterday you were explaining. So yesterday you had explained what a concentration cell is, but what are its real life applications? Where is it used?
Concentration cell, we can say in the cell walls, for example, when the electrolytes are admitted inside, outside, right? See, the sodium goes into the cell wall, comes out. It's by the principle of that potential difference. Okay, but in real life, there is no application that we have for this, because the EMF difference, the EMF that we get is very less. Okay, so we don't do that. But in principle, you can use, if you have extreme concentration difference, you will get a very good EMF, then you can make it as a cell. Yeah. So, but in real life, we don't do that. Real life, we have two reactants which are very distinct. They are not the same redox couples, right? Yeah. But this is a best example to understand, EMF, the same electrode is given, which one will act as anode, which one will act as cathode, all that we could understand with that. But to my knowledge, there is not application that you find. Yes, is it glowing? Yeah.
Yes, sir. Sir, Daniel cell, zinc and copper is there, no, sir. According to Nernst equation, what will happen if concentration of copper is reduced or increased?
Reduced?
Or increased?
You should again apply the Lee-Charles principle and check what will happen.
We can apply Lee-Charles principle.
Yes, that's what we should do. For example, here, let's draw zinc. So I have a zinc sulfate, say 1 molar, and then this is connected to a salt bridge. So I have a copper sulfate, say 1 molar, I have copper, and you know the potential of this is 0.34, potential of this is about minus 0.76, both with respect to standard hydrogen electrode, correct? Yeah. So what is E cell? E cell, when in galvanic mode, is E cathode, E anode. What is cathode here? Cathode is the one which has a higher potential, which is 0.34 minus of minus 0.76, that's about 1.1 volt. Now imagine you are going to increase the concentration of zinc sulfate here, you are going to add some zinc sulfate. Then what will happen to this equilibrium? You have added this, which way equilibrium should go? This way. That means zinc oxidation will slow down. Yes or no? If the zinc oxidation slows down means what? The equilibrium goes this way. That means in galvanic mode, zinc is oxidizing, copper is reducing. Now by adding zinc sulfate, the efficiency of your galvanic mode you are reducing. You are making sure zinc oxidizes slowly now. You are not letting it go, because you are adding zinc sulfate and you are shifting the equilibrium towards this. We can verify it using the Nernst equation. Let's do that. So Nernst equation E cathode is this, so that's going to be 0.34 minus RT by NF ln reduced form is copper, activity is 1, copper 2 plus is 1 molar, so I take 1, right. So this term will disappear and then minus of minus, so that's going to be minus 0.76 minus RT by NF, N is 2 here, ln reduced form is zinc, activity is 1, zinc concentration to start with is 1 molar, correct. So now this term also will disappear because ln 1 is 0. So then what you get is this and 1.1 volt. Now what you are going to do, you are going to add zinc sulfate, that is what you said. Zinc sulfate means you are going to increase the concentration of this. So this is going to be 1 plus some delta. So this is a bigger value, then it will become minus 0.76 minus, so this is going to be about 0.03 times log of, say, if I say just for argument's sake, I make it 10 molar. I make it 10 molar, this one. So then it becomes minus log m minus, then it will be plus log 10, correct? So log 10 is 1. So you are going to then shift this fellow by 0.76 plus this much voltage, 30 millivolt. 30 millivolt is gone, means this is going to be minus 0.73. This side is 0.34 minus of minus. That is going to be how much? It is going to be less than 1.1 volt. So you are going to get how much less than 30 millivolt less? About 1.07 volt, correct? So you see your EMF has come down. The EMF has come down, what happened? The driving force is less now. So reaction will happen slowly for the given resistor. So if you put a resistor here, you are going to connect it, you are running the cell, okay, before adding zinc sulfate, after adding zinc sulfate. Before adding zinc sulfate, particular amount of current will be flowing. Now by adding zinc sulfate, you will slow down the current flowing. That means less current will flow now. Why the EMF is less now? So across this resistor, earlier what was dropping is 1.1 volt. Now across the same resistor, what is dropping is 1.07 volt, right? Therefore less driving force means less current will flow. We can understand why less current flows is because you are actually shifting this equilibrium. This is by Lee-Chatterjee principle, correct? Next. If you have some question on thermo or kinetics also, you can ask. Yeah.
Sir, you had mentioned about the transport number for an ion. What decides the transport number? Like,
that is the intrinsic property of the ion. As I said, the size of the ion, charge on the ion, and size means it includes the including the solvation. Okay, size of the ion, the charge on the ion, and which medium it is moving. It's a viscous medium or it's a very dilute medium. Depending upon that, the value will change. So it is something related to the intrinsic property of the system. Then good catalyst. See, generally, let's look at this fuel cell reaction. So hydrogen, it will oxidize. So same time, the oxygen will take that proton and the electron will come from the external circuit and it should become O2 minus. So it's going to be H2O. It's going to be H2 plus half O2. Correct? This is your fuel cell reaction, and you know the potential of this is 0. This is 1.23. So E cell is 1.23 minus 0 is 1.23 volt. E cell is positive. That means hydrogen oxidation, oxygen reduction should be a spontaneous process because delta G for that is negative. But you take hydrogen in the laboratory, just leave it outside, there are a lot of oxygen here, then you should see wherever the hydrogen encounters oxygen, a water formation, but it does not happen. Do you see that? It does not happen. Why? Why it does not happen? Because thermodynamics says it should happen, right? Then it should happen. Activation energy. So we have discussed about kinetics. What was your question? Why D block element acts as a good catalyst? So in this process, in order to decrease the activation energy, we are going to use a D block element. What is the D block element here? It's a platinum. So we use platinum. Platinum's 3D, if you look at the platinum, and then on platinum's surface, we are going to absorb this hydrogen and oxygen. I told you earlier, if something absorbing on something or a surface, that means the orbitals in the surface of the material must be overlapping with the orbitals of that species which is absorbing. Okay. So if you look at in the platinum, so what is the atomic number? 1 platinum. I think its atomic weight is 195. Atomic number is how much for platinum? Can somebody quickly find out? You have 78. That is like 78 means it is 4F 14 5D 9 6S1 something like that, right? That's what I see for platinum, right? So, so if you look at it, you still have some orbitals which are half filled or partly filled, correct? So these are the guys who will be interacting when the hydrogen comes to the surface. So when these hydrogen orbitals interact with them, when there is a symmetry, when there is a favorable interaction possible, that is when the hydrogen will absorb. Assume that now we have a catalytic surface on which hydrogen absorb. If hydrogen is absorbing, either the surface must be donating electron to this or this hydrogen must be giving electron to this. Something should happen of that kind. Okay, because you have hydrogen, it gives 1 electron, this gives 1 electron, so bonding orbital has a 2 electron, anti-bonding orbital has no electron, correct? Yes or no? You know this, right? That's there, the plus 1. So if I add any electron here, the bond order will decrease. What do you mean by decrease in bond order? When you add any electron in the anti-bonding of this molecular orbital of hydrogen, then you will see this bond will break. Why bond order decrease? That means the bond will stretch. Decreasing bond order means what? There is one bond. How will you make that one bond into fractional bond? One way of thinking is like you are stretching it and it's becoming weaker and weaker and weaker. There is a less attraction force between them. So when this fellow is absorbing on platinum, it will give electron. This guy will receive that electron. Because this guy also wanted to go to something similar to octet. It's not octet because you are going to 5D orbital and so on. So it will accept electron in this case, for example, while absorbing. Then what will happen? So then, or if this also can alternately give electron. So if I assume that this is giving electron, if it goes here, then what will happen? This bond will break. Then you will have an overlap between the orbitals of the surface and the orbital of this hydrogen atom. Because when you talk about solid state materials, we don't talk about orbital, we talk something called bands. Because there are n number of Avogadro number of atoms. So when you combine them, you get something called bands, valency band, conduction band, and if it is a metal, there will be an overlap between these two bands. So you will have something called Fermi level, correct? So now if you look at it, so this hydrogen will get absorbed like this, but since an electron is added here, this guy might break. Why? Because bond order will decrease. So the hydrogen molecule now dissociates into hydrogen atom, but it is not simple hydrogen atom, it is attached to platinum. It's like a covalent bond. This fellow gave 1 electron, the surface gave 1 electron, this fellow gave 1 electron, surface gave 1 electron, so it becomes something like that. Now imagine next to it you have oxygen coming and absorbing. So oxygen also has got a double bond. Same principle here. So when there is an interaction, it can get absorbed. Oxygen can absorb through end, that means one of the oxygen can absorb, one may be dangling, or both oxygen can absorb, that is side on absorption. Some absorption will happen. Once these guys are in very close proximity, because this is one platinum atom, this is the next platinum atom next to it. What is a gap? It's in Armstrong, few Armstrongs, right? So very close to each other they are. So now what will happen? Now the orbital of this guy and this guy, they are seeing close to each other and they are immobilized, they are not moving. So when something is close, it is easy to exchange energy between them, correct? So basically this surface can switch its oxidation state. How it is switching? Either giving electron or to the species outside or taking electron from the species outside, it can do that. So for a moment these guys are immobilized on that. Once they are immobilized, between them there can be a reaction. and that is what finally gives you water. Once it forms water, all this water doesn't have any absorption on the surface, so it just get out, leaving again a free platinum surface on which further hydrogen and oxygen molecule will absorb. So basically, if you see any catalyst, generally a catalyst will be something which is having ability to accept and donate electron. That property comes generally in the d orbital, d block elements. So therefore, this is not the, I am not talking the bulk platinum is receiving, the surface platinum at least is doing this. So therefore, you have this electron exchange. So the species are adsorbed very close to each other, in this case hydrogen and oxygen, and they have a chance to react. Basically, this is not a direct reaction of hydrogen and oxygen by collision. It is some sort of immobilization of these two species, and they diffuse in the surface only where it is absorbed and then react. Correct? So it's a totally different route by which hydrogen is encountering oxygen. Therefore, the activation for this process is lower compared to straight hydrogen oxygen collision. So that's what catalyst is supposed to do. Catalyst is supposed to give an alternative route by which the same reaction can happen. But still all the equilibrium principles are valid here. Only thing is the catalyst will get you to the equilibrium faster compared to direct hydrogen to oxygen. Therefore, if you take hydrogen and oxygen, mix in a bottle and then wait for a billion years also, you won't see any water drop forming. Whereas you put a platinum foil inside and then pump hydrogen and oxygen and see, you will see immediately water forming. Why it forms? Because the surface catalyzes that. How surface is able to catalyze it? Because this has a redox property. We can accept, donate electron, allow the electron to exchange between them, because this is conducting, right? Electron can flow within them. This is a route. Electron can come from here, go here, right? Through the bands of the platinum. This is how they do. So this is very qualitative way of saying. If Professor Mangalasundar is doing this, he will look at the orbitals, actual orbitals, what is the extent of overlap between the hydrogen and this orbital, oxygen and this orbital, how this reaction happens. All those predictions they will do, and what will be the what should be the structure in the surface, mean the facet in the surface, because we take a platinum is FCC, phase centered cubic lattice. So I told you yesterday something we briefly discussed, what is 111 phase, right? What is 111? 1 unit along X, Y and Z. So that is 111. So imagine you are slicing in this direction, okay? Then the atoms that you see in that sliced surface are the atoms belong to 111 plane. Now if you look at the atoms in this front face, okay, what is that? They are only 1 unit along X. They are parallel to Z, they are parallel to Y. Such things are called 1, 0, 0 plane. Whenever it is parallel, we put a 0, 0 there. Okay, so it is 1 unit along the X and it is parallel to Y, parallel to Z. So it is 1, 0, 0 planes. There is 1, 0, 0 plane here, there is a 1, 0, 0 plane here, there is a 1, 0, 0 plane there, there is 1, 0, 0 plane there. Since it is a FCC lattice, 1, 0, 0 is identical to 0, 1, 0, identical to 0, 0, 1. That means this face is same as this face. This face is same as this face. Correct? So, if you look at it, whether you have 111 surface, whether you have 100 surface, the number of atoms in that surface and the gap between the atoms will vary. Correct? No? So, that means the 111 surface of same platinum will catalyze differently compared to 100 surface of the same platinum. Correct? Yes or no? So, the kind of termination, that means what facet is there on the surface of the particle, decides also the activity of this reaction. Okay, right? So, a theoretician will look at that way. Imagine I have a particle which is having only 111 surface, all the sides. A particle which is having only 100 surface. Then what will be the activity for this hydrogen oxidation, oxygen reduction? Correct? So, there is a more in-depth thing, it's all research problems, but you see same catalyst, a different surface has a different. That is why sometimes you will see, say you commonly what you do is hydrogenation reaction using Raney nickel, correct, no? And you use a nickel for hydrogenation reaction, right? Suppose you also make a nickel, you also make a nickel in the laboratory, but you don't see the rate of the reaction is not same, although you are putting same amount of nickel. That means the among the particles that you got, the fraction of particle which is having 111 surface may be different from what you have prepared. Therefore, the average activity is very different, because you might have used a different synthetic route, she might have used a different synthetic route. You got the same 1 gram of say nickel both of you, but same particle size also may be same, but the phase set may be different, that is exposed. So, the activity will be different, right now. So, generally when you make a powder which is having all kinds of phases 100, 111, 200, 1 depending upon there are some crystallographic rules are there based on that. For example, if it is FCC, so generally we have everything odd or everything even kind of phases possible. Okay. So, all that everything odd, everything even is possible, but to see by XRD, but you have all kinds of phases like 100 or 200 or 111 or 121, right. So, all that matters, right. Extra diffraction is there or it is removed? Extra diffraction are there. Any other question?
Sir, how are these phase sets being determined by the synthesis, sir?
By synthesis, there are many factors. For example, you can have some sort of what do you call this, capping agent, which is an organic molecule. So, you can add them like citric acid, you can add them during synthesis. Citric acid kind of go and complex with that nucleus which is forming during, suppose you are synthesizing a metal nanoparticle. When the nucleus say gold nanoparticle you are forming, the citrate will go complex with the atoms, the surface. So, depending upon whichever the phase set having affinity to the citrate, to that phase citrate will go or citric acid will go. Remaining phases will be exposed. Therefore, when you grow the particle, what will happen? The growth in that direction will be enhanced. Imagine very simple. I have a citric acid and I have a particle that is forming just starting. Imagine that particle has got also 111 phase, in the other side it has got 100 phase set. Now imagine this phase set 111 side has a lot of affinity with citric acid. Then the citric acid tend to absorb on this surface. If citric acid absorbs here, now if you want to grow this particle bigger, then you have to bring another gold ion and reduce it on its surface and attach to it, right. How are you building? First you make one gold atom, on top of that you will attach another gold atom, like that you grow the particle, correct. Now what happens? This phase set which is formed initially has good affinity with the citric acid, so they go and stick there. Then you are left with the other surface. There it is still possible to assemble the gold atoms. Then what will happen? When you are continue to synthesize, that means you add a reducing agent to reduce gold ion, auric ion into gold atom. They continue to deposit on the surface where there is no citric acid. Then what will happen? Particle will preferentially glow in one direction. So you will have only 100 phases more than 111, because the 111 is already getting blocked. This is one way. So depending upon your synthesis condition, what is there in your solution, so that will decide what kind of distribution of the phases will happen in a particle. If you look at through an electron microscope, you will see particles of all kinds of shape. It won't be uniform, always it won't be spherical, always it won't be cube. It can be all kinds of things. But if you are having such agents in your synthesis, you will see through electron microscope, all the particles will look alike. All of them will be looking like a cube, all of them may be looking like a triangle. How we are able to make a particular shape of the particle? It is because you are blocking growth in the other direction. Therefore, you will be able to make it. For which this is called capping agent. Capping agent will cap, and that place there won't be any growth. The other places you will have.
What are the capping agents to determine the shape of protein takes?
Protein, I have no idea. I am not an organic chemist. But what is that your question? Protein synthesis?
Protein synthesis goes beyond about capping agent.
Maybe you are talking about blocking the amine side or carboxylic terminal, right? There generally in organic chemistry, when they talk about, suppose there are two ends, amine end, carboxylic acid end. Suppose they don't want to grow in this direction, they want to grow in this direction only. But there is a probability, if you add another amino acid, it can go there also, here also, because the amino acid has got amine terminal and carboxylic acid terminal. So that can go add that side or it can go add this side. So I don't want that to go that side. I want to go in. I want to grow in certain sequence, and that should go only in this direction. How will I do that? I have to protect that carboxylic acid group. So I have to do some reaction and protect that carboxylic acid group, so that this condensation will not happen there. So that only opportunity is to grow from this end. This is also called capping. After completing the sequencing, they will go and then release that capping agent. Then you got what you want. Basically, it's the same principle as here. Here we are talking about on a particle, there you are talking about on a molecule. One side of the molecule you stop growing, only one side you can grow. To do that, what we have to do? We have to change the property of this functional group. We have to change that functional group. Suppose acetic acid functional group is there, you convert into some sort of protect it with the methyl group or something, so that it doesn't grow. So only one side grows, right?
Sir, yesterday we had talked about the concentration factor W and the Arrhenius equation. The Arrhenius equation bit I'm still confused because.
Okay. So you are going do this reaction, okay? So how will you write the rate of the reaction? Rate of the reaction you write it as a K times A if I assume it as a first order reaction. Generally we don't know the order. If I assume it is a first order, then it's 1, right? So now what is this K? This K is dependent on few things. One is frequency factor. Other one is the activation energy involved in the process of converting A to B. Okay. What is this frequency factor? I told you the number of successful, number of times, the molecule collides per unit time. Okay. Because for a reaction to happen, there should be a collision between the molecule. So number of time it collides per second. It's like a frequency factor. Why is frequency? Frequency as a unit of 1/second. So this also has a unit of 1/second. That's why we call it as a frequency factor. Which is that frequency? This frequency is nothing but the collision frequency. Because we are talking about reaction, right? Collision frequency, and this frequency is the frequency at which A can be converted to B can be equal to W, provided if this term becomes 1. Correct? No? When this will become 1? This will become 1 when A is 0. When activation energy is 0, e power 0 becomes 1, then the frequency factor or the frequency at which A is converted to B is nothing but frequency factor. Correct? No? But generally A has some finite value. So this term here is kind of modifying this frequency factor. This term will reduce the value of the whole thing will reduce if you have some value for A. Correct? Suppose I have a frequency factor of 100. So e power 0 means it will be 100. If it is e power minus 1, it will be less than 100. If it is e power minus, it will be much less than 100. Correct? So this kind of decides what is the value of the K. Okay? The K is a rate constant. So the rate constant depends on what is the activation energy involved in the process. Also, what is the frequency with which something colliding. Right? That's what we discussed yesterday. I extrapolated this multiplying by N and F into a current density. Right? Because when you talk about rate of the reaction in kinetics, we call it as a current density in electrochemistry terms. Any other question?
Sir, in thermodynamics, we make use of a term called Helmholtz free energy, right, sir? Where do we actually use it, like for measuring, or where do we use it, sir?
You are already doing calorimetric experiments where you are measuring enthalpy change, right? You are doing wherever there is a heat energy involved, wherever there is an energy matrix involved, there and all you will use data H. One simple experiment you do in the laboratory is a calorimetric experiment.
What exactly is that energy compared to all the other energies?
What exactly is that energy? See, if you look at in thermodynamics, suppose if you are combusting something, say we have a fuel, say methane, we are combusting into oxygen. What happens? methane, because we are doing it, all of us go do cooking at home. So we have the Indian gas. So say that is not methane, but maybe the higher order carbon, but let's assume it is a methane. So then it becomes CO2 plus 2H2O, correct? It gives also flame and also heat, correct? So you have a flame associated with that heat and so on you are having when you are cooking, right? So where does this energy coming from? This energy actually coming from the breakage of this bond. So you have to balance this 2 oxygen, 2 oxygen, 2 O2. So this energy coming from the breaking of this bond. This we call combustion. By combusting this fellow with oxygen, basically it's a battery. You can imagine methane is a fuel, right? Oxygen is a reductant. Oxidant. So this will give electron and this fellow will receive electron. So imagine you can this like an anode, this like a cathode of a battery, in sense, right? Same. So the energy stored in this fuel is extracted, okay, during this burning process or combustion process. That's what you are getting, and that's the energy you are measuring. If it gives enough calorific value, what is the calorific value? How much heat you get, how many joules you get per gram of this, right? How many joules you get per gram of this. So depending upon the hydrogen content in this, that will increase or decrease, right? No. Suppose I have a carbon, I am burning carbon into carbon dioxide. So this will have a certain calorific value, right? Therefore, when you say coal, we don't use every coal directly into our thermal plant. We need to ensure the coal has a less ash content. Why? Because you are adding 1 kg of a coal. Suppose in that half kg is ash or some inorganic fillers in that. Then what will happen? Your calorific value come down. Correct? No, or if it has moisture, calorific value come down. Why moisture will reduce calorific value? Because the water will take the heat. Because water has high heat capacity, it will take the heat. It will not let the heat go out. That means the amount of work you can do with the available heat is less now. Therefore, calorific value is very important. So the measuring calorific value is one place where you use this enthalpy, all this thermodynamics thing, right?
So yesterday we talked about lithiated graphite, right, sir? Do we use a capping agent to produce lithiated graphite?
Why should you use capping agent there?
Like to block the lithium from going to the other sides of the sheets?
Oh, okay. You are worried as if lithium will flow through the gap. It's not going to happen.
How do we like stabilize lithium?
Because there is
in
an
the center?
interaction. Because there is an interaction between the graphene layer and lithium. Because the graphene layer is holding the electron. Lithium is here. So this electron is here, the lithium cation is here. Then there is a coolostatic attraction. So it cannot get out. If it gets out, it has to take the electron also and get out. It cannot just like that get out. So there is an invisible force which is controlling them. Right? Any question? Yeah. Switch on. It will come. Light will come.
So I've heard about it. I don't know if it is true. Is it possible to generate energy from smoke, like from factories and all the smoke that evolves?
It depends. Suppose your smoke has a lot of carbon. You can burn carbon, make energy. Suppose if your smoke is very hot, you cool down the smoke, extract the heat. Extracted heat can be used. Anything people see, people even say water battery. There is no sense in that, because these are all some guys who doesn't, they are interested in projecting everything using some kind of buzzword rather than by actual science. Okay, so I am not a big fan. How can you have a water battery? Water itself is a very stable product. As a result of hydrogen and oxygen, you got that, right? So you already extracted energy. Then what? How else you can extract energy from water now? You cannot. Correct. So, but people write like that articles, right? But anyway, you have to be careful. That's where you have to apply. From smoke, yes, certainly possible, provided what is the smoke composition? The smoke composition is full of carbon or soot, yes, you can burn and make still energy. Or the smoke is at high temperature right now, then you can interface it with something which can extract heat and use that heat for something. It's possible. So again, all kinds of smoke can give you that, right? Not possible. Anything else? Yes.
So, could you explain a Hithouse method to calculate the transport number?
Hithouse method. Do you have a textbook now? I don't remember some of those. You have your textbook here? No? Basically, they use some colored ion to measure the distance it flows in a given time and things like that. Okay, Hithouse method is a 3 compartment. The 2 compartment, the center compartment there won't be any concentration change, and there are 2 extreme compartments where there is a reaction that goes on. That is what Hithouse method. I don't remember the name and what is that they do. If you have a textbook, I can look at it. No? Or let you know in the next class if I don't. Next. So now let us look at little bit on this. I think Hithouse method is the same thing that what I am talking about. You have a central compartment and there are 2 extreme compartments. You have the solution here whose concentration doesn't change with the time, and you have a 2 different concentration of solution here, and you do electrolysis if I am right. But anyway, I'll check it and get back to you on that. Okay. So now, so liquid junction potential you all understood yesterday, right? How it arises, correct? And we need to make measurements without including the liquid junction potential. That is why we are using the salt bridge, because the salt bridge has got the salt which has nearly similar, the anion and cation of the salt has a nearly similar transport number. That means their current carrying ability is equal. Okay. So that's why it is doing it. Okay. In reality, how we will make a battery? Are we worried about this liquid junction potential and so on? It is not. In reality, we don't care about that. In reality, for example, if you are taking a fuel cell, in fuel cells, as I said, we have a porous electrode. That porous electrode is coated with a platinum particle. Okay. And then we have a in the modern fuel cells has a solid state electrolyte. Okay, it's a polymer electrolyte basically. It doesn't have any liquid electrolyte. It's a polymer electrolyte. So the polymer electrolyte has got a polymer backbone. Okay, like a Teflon. Imagine what is Teflon? Tetrafluoro ethane. I mean polytetrafluoro ethene. Right? You take this fellow. You have to polymerize this. This is polytetrafluoroethylene, right? So this guy you polymerize it, you get that. Imagine you pull out one, so this is going to be your polymer. So imagine you pull out this sulfur and you connect it with some sulfonic acid group. Okay. So you have a side chain which we call it as a pendant group. We put a pendant group of sulfonic acid here. So the sulfonic acid group is the one which actually does the proton conduction. So there will be lot of sulfonic acid groups here in this polymer. Okay. So these are the ones which conducts a proton for us. Okay. Now you put another electrode here, which is again a platinum electrode. So there is a lot of platinum particle here, and this is again a porous electrode. Now you pass hydrogen from here and oxygen from here. Through these pores they come to the catalyst point, and the catalyst is in touch with the proton conducting membrane, and again which is in touch with the catalyst this side. So as I told you, the hydrogen oxygen has the ability to adsorb on the platinum, and then both the electrodes, when I connect, they will see potentials of each other, and there is a again the same Richard principle will apply in terms of potential, and you see the equilibriums are disturbed, current will start flowing. Correct? Now there is no question of transport number here. Why? Because the membrane can conduct only proton. What are the ions involved in this process? If you look at it, hydrogen oxidizes to proton plus 2 electron, and simultaneously oxygen reduces to oxide ion, right? Oxide ion plus 2H plus, this is nothing but water, correct? Right? So now you have oxide ion also, or if it is an alkaline medium, you will have OH minus ion also, right? So now we have oxygen also, proton also, but only proton will move now. Why only proton will move? Because this has to go through this polymer. This polymer can conduct proton from one side to other side. It's an ion selective membrane. So in that case, what will be the transport number of cation? 1. Transport number of anion has to be 0. Because by the design, I will not let the anion move. It only the proton which can move from one side to other side. Therefore, you don't need to worry about transport number here because the transport number is 1 here. Right? And now in this case, where is the salt bridge? There is no salt bridge because the real device we don't make with the salt bridge and so on. We will make it like this, as simple as possible. Very thin electrode of anode and cathode separated by a thin membrane. That's it. This is how the entire thing will be something like less than 1 millimeter or so. That's one cell. Thickness of that is less than a millimeter, one cell. Okay, like that you see 100 cells you put, you get. So each cell gives 1 volt, then 100 cells in series will give you 100 volt. So you'll have a 100 volt stack this big. Correct? So this is what happens. Again, where from the electron will start? Electron will start from here and it will end up here. Correct? Because this is oxidation, this is reduction. This is how we make. And let's go to the lithium ion battery. In lithium ion battery, how do we make? Again, there is no salt bridge, nothing. We have lithiated graphite. And we have in the interface the electrolyte, but here we will use a liquid electrolyte. It's called propylene carbonate or ethylene carbonate. It's all cyclic carbonates, propylene carbonate or ethylene carbonate, in which we will dissolve a lithium salt, lithium hexafluorophosphate. Lithium hexafluorophosphate, right? So you have this salt dissolved in these things, that is your electrolyte. And yesterday we have explained why we are not able to use aqueous medium. When you are trying to charge this battery, instead of lithium ion reducing to lithium, you will have proton reducing to hydrogen first. That means all the water will dry out. You cannot make a battery with this. Even lithium will not be compatible with water because lithium will react with water. Right? When lithium reacts with water, lithium is oxidizing. What is oxidizer here? Water. What in water is oxidizing? Huh? What in water is oxidizing lithium? Huh? Proton. Proton in water is what taking the electron from lithium, right? So, not necessarily oxidizer should be something like oxygen or peroxide. It depends on the energy levels. If lithium is there and the water is here, then water also can be an oxidizer for this. It can take electron and produce hydrogen, correct? So, this is what will happen when you are going to lithium ion battery. We need to have a non-aqueous medium. That will take care of these issues. But there are issues with this because when the temperature goes up, this can be a volatile compound, and if there is an oxygen present in presence of lithium and oxygen, this can catch fire. That's why you see a lot of battery catching fire and so on, because it's very dangerous, because any organic liquid there itself is a fuel. Any organic liquid, because it has got hydrogen in it, right? So you can burn it and make energy. Yeah.
So can you repeat the compound name, please?
Ethylene carbonate and propylene carbonate. Electrolyte only. Lithium hexafluorophosphate dissolved in ethylene carbonate and propylene carbonate. Right? So depending upon the issues in the battery, we will choose the materials accordingly. Okay. For lithium and sodium batteries, we have to use a non-aqueous medium. For a hydrogen oxygen kind of a thing, we can use aqueous medium. For example, aluminum. You cannot make aluminum rechargeable battery. Why we cannot make aluminum rechargeable battery? How aluminum is made? So that is in the metallurgy chapter. That also comes second year, I think. From the bauxite, what you do? You have to do? What is the process called? What is that process? What they do in that process? It's called molten electrolysis. Molten electrolysis means you have an electrolyte which is solid at room temperature, but you have to apply heat. You have to heat it in order to melt it first. The molten electrolyte will form once you melt the salt, right? And then you will have anode and cathode. In the molten solution, you will do the electrolysis because ions has to move, right? So, in the molten solution, you will do electrolysis. Molten electrolysis. Why can't we do aluminum extraction at aqueous medium? not possible. Because if you look at the aluminum 3 plus redox couple potential, it is much lower than the hydrogen. So if you try to do it in water, what will happen? Again, hydrogen will come out first. Aluminum salt will not reduce at all. Correct? But you can make a aluminum air battery in water which can be used as a primary battery. What do you mean by primary battery? Let aluminum oxidize, because aluminum has a more negative potential than hydrogen. Therefore, aluminum will be more reactive than hydrogen. Therefore, when you are using it as a primary battery, you can use water. Aluminum will oxidize, and then you will have the other side. If you pump oxygen will reduce. Then you have a aluminum oxygen battery. If enough oxygen not there, it will become aluminum hydrogen battery, because the electron that goes from the aluminum go to the other side, reduce the proton in the water. Okay, but then voltage will reduce. But if you have oxygen, voltage will be a larger voltage, right? So it can be a primary battery. It cannot be made into a secondary battery. Why? Same limitation, right? So if you want to make aluminum secondary battery, obviously you have to go for a non-aqueous medium. Primary battery, yes, it is possible, right? Similarly, zinc air battery can be a primary battery for sure, no problem. If we are using it as a secondary battery, there are issues, because zinc also has a potential negative compared to hydrogen redox couple, hydrogen proton redox couple, about minus 0.76 volt. So when you are charging, you have a problem, but it is not too far from the hydrogen value. Therefore, considering the over potential that is playing during the reaction, we can still make zinc metal in aqueous medium from the zinc salt, but you can't do it for aluminum or lithium salt. From there, lithium or aluminum you cannot produce, right? Any other question? How copper is made? Pure copper. How pure copper is made? That means I give you impure copper. From there, I will make pure copper. Electrolysis. Somebody asked me what is the practical use of concentration cell in the beginning. Correct? This is a practical use. So the copper, impure copper is one side, pure copper in one side. They are different in their activity, right? Pure copper activity is 1. Impure copper cannot have activity of 1. So it is a concentration cell. So you can dissolve the impure copper and then deposit that copper in the pure side. Then you will have a copper refining. Okay, an impure copper rod is made into a pure copper rod. Correct? This is one way. So likewise, there are many metals which are purified this way by electrolysis method. Right? Correct? Anything else? No question? Okay. If there is no question, then you will see in the next class. Because now you exhausted your question, when I come for next class, I will bring with my video content. Generally, I don't do that. If you have a question, I try to answer. Okay? Good. Good luck. Thank you, sir. Yeah.